Hi there, in this video we're going to bring everything we've looked at so far together and we're going to look at how we can define a little bit more generally what multiplication looks like with matrices more generally, moving away from these 2 by 2 transformation matrices. So the first thing we're going to do is just recap. So let's just recap what we've seen so far. So far we've looked at a matrix as a transformation of a vector, and you'll remember that this vector here was where the image of I hat was where I hat ended up, and this vector here was where j hat ended up. So let's just do this through an example. So let's look at 1, 2, and let's look at 2, 3. Okay, and you'll also recall that if we have the vector 3, 4, before the transformation, that just means we've got 3 I hats and 4 j hats. Okay, so that's sort of setting up the problem. And then we looked at the fact that, well, because this vector before the transformation was 3 I hats and 4 j hats, and because these were our basis vectors, it makes sense to think that after the transformation, it'll turn into 3 times by the image of I hat and 4 times by the image of j hat. So if we're going to do that, we would get 3 times by 1, 2, and we would get 4 times by 2, 3. Okay, and then when we work through that together, when we work up through all of that, we get 3 times 1 and 4 times 2. So 3 times 1 and 4 times 2. I'll do that in blue. And then 3 times 2 plus 4 times the 3. Which we could work out into a final vector, but just to sort of so we can see where it's coming from, I'm going to leave it there for now. Yeah, so then that's sort of what we would say this matrix is equal to as a multiplication. And that led us to this idea that if we offset our matrix like so we had 1, 2, and we had 2, 3, and we had 3, 4, then if our answer is here, then the top number is going to be this row times by this column, and the bottom number is going to be this row times by this column as well. We also saw that we could extend this to doing it with more than one vector at once. So if we also had a different vector, 1, 2, 0, 3, and 4, 7. So if we had 4 vectors that formed a square, and then this entry here, we'll do that in blue for consistency, this entry here is this row times by, or this column times by this row, and this entry here is this column times by this row, and so on. Okay, so this idea of transformations has led us a little bit of a, through this journey, and we've landed at this idea that we can multiply a 2 by 2 matrix, a transformation, by a series of vectors. And it turns out that this method actually works generally for many different types of matrix. So in the next example, we'll have a look at when this doesn't work, first of all, and we'll have a look at exactly how to apply this to bigger, smaller, and different size matrices. Okay, so before we go any further, I think it just is worth just having a quick recap and a quick sort of run through of what the algorithm is and what that might look like for general matrices. Okay, so the first thing we said we needed to do when we're looking at transformations of lots of different vectors is to help with visualization. We're going to do a little bit of working out by the side, and we're going to offset this second matrix so it sits above the first matrix. So 1, 2, 0, 4, minus 1, 2. Let's offset that. Second one, so we've got 1, 0, 1, 2. Okay. Yeah, let's just make that bracket a bit better. Okay, so then our answer goes in the middle here. And our answer is going to, we can see straight away from this method that our answer is going to have 6 entries in it. And our answer is going to be a 3 by 2 matrix. Okay. So let's have a look then at this red entry here. So it's the top left one. So we're going to do the top row of the first matrix times by the left-hand row of the second matrix. And we're going to multiply, and when we say we're going to times them together, and we're going to work from the outside towards the centre, and we're going to multiply them as pairs and then add the answers up at the end. So we're going to do 1, I'll draw the lines on just for this one so you can see what we're doing. So I'm going to do 1 times by 1, that gives me 1. And I'm going to do 2 times by 1, that gives me 2. And then when I add those together, 1 plus 2 is equal to 3. Okay, so we multiplied them in pairs, added them together, and that gives me that entry. Okay, let's have a quick look then at what's going to go in this top right one here. So we're going to do this row times by this column. So we're going to get 1 times by 0 is 0. We're going to get 2 times by 2 is 4. So the number that goes in this column, or this entry, is 0 plus 4, which is just 4. Okay, let's look at this number here. So this number, we're going to do this row times by this column again. Okay, so again, working our way inward, we're going to get 0 times by 1 is 0, and we're going to get 1 times by 4, which is 4, and again, 0 plus 4 is just 4. Similarly for this entry here, it's in blue, we're going to do this row, the one that's in line with it, times by this column, the one that's above it. So we're going to get 0 times by 0 is 0, 2 times by 4 is 8, 0 plus 8 is just 8. Okay, so last two now. So here we're going to do this column times by this row, minus 1 times by 1 is negative 1, 2 times by 1 is 2, and negative 1 plus 2 is just 1. And then finally, this entry down here, minus 1 times 0 is 0, 2 times 2 is 4, 0 times 4, or 0 plus 4 I should say, is 4. So this is our answer, this is our final matrix. So we're over here in our main body of, in our main answer to the problem, we can do 3, 4, 4, 8, 1, 4. Okay, so there we go. So that's the formalize it. That's sort of, a more, I suppose, rigorous statement of the algorithm, a more general statement of the algorithm. It's still not particularly rigorous, but it's a more general statement of the algorithm that we can use to multiply these vectors. And it turns out that many of the other applications of matrices, so when you look at graph theory, you can encode information about how different points connect to each other, which is important for maps. This method of multiplication still has a lot of meaning in those other applications as well. So let's have a quick look at when this method maybe breaks down and when multiplication isn't defined with two matrices. Okay, so let's have a look at this multiplication here. So we've got two matrices, they're both the same size, which might trick us into thinking that we can actually multiply these. But when we try and multiply these and look at the algorithm that we came up before, we'll come a little bit unstuck. We'll notice that something's not quite right. So what we'll do is 1, 2, 0, 3, minus 1, minus 2. Remember, we offset that matrix up So we've got a space for our answer here. 3, 6, 1, 2, 4, 9. And our answer is going to go in here. And again, it looks like we'll get 6 entries if we can multiply these. So let's have a look at how we do it. So if we're going to multiply these, let's work at this number first. That's going to be this row times by this column. And again, I'll draw the arrows on like we did before. So if we're working our way from the outside towards the number, we're going to get 1 times by 3, which is 3. We're going to get 2 times by 1, which is 2. But then we come into a problem because this 4 doesn't have anything that it can times by. So this one is not defined. Doesn't make sense. We can't multiply these two matrices together because they're not the right size. So I'll just take a few seconds to have a little bit of a think about what needs to be the case for us to multiply these two matrices together. It clearly isn't that they're the same size, but just pause the video if you need to have a little bit of a think and maybe try and explain in words how we know if two matrices can be multiplied together. Okay, so what we'll do is we'll look at two sort of ways we can check to see if these matrices can be multiplied together. Okay, so the previous example that could be multiplied together, I can't remember exactly what it was. Let's say it was that. This one could be multiplied. This one worked quite well, but this one didn't. And we know it's got something to do with the sizes. So let's write the dimensions down. If you think back to the very first video on this, let's write the dimensions down of these two matrices. So remember, we do the height by the width. So the dimension of this matrix is 3 by 2. And the dimension of this matrix is also 3 by 2. Okay, so for this method to work, for us to be able to pair up the width of the first matrix with the height of the second matrix, these two numbers in the middle have to be the same. If they're not the same, then we can't multiply. Whereas here, the first matrix was still a 3 by 2, but the second matrix was a 2 by 2. So in this case, because they are the same, we can multiply them. Okay, and you'll recall that the answer we got for this matrix was a 3 by 2 matrix. And you might spot that the 3 by 2, it's this and this. So the first and last numbers in our dimensions tell us what the answer, or what the dimensions of the answer is going to be. 3 by 2, 3 by 2. Okay, the other way we can think about it, and let's call this method the happy square method, which certainly sounds like it should be certainly lower down score than when you're dealing with matrices, but it's always helped me remember this is the method I learnt when I was in school. If we try and do the multiplication, 1, 2, 0, 4, minus 1, 3, 1, 1, 2, minus 1. We've obviously got the space for our answer here. That's where our answer goes. But here, we'll get a shape. And if that shape's a square, it means that the width of this first matrix by the height of this second matrix is the same, if that's a square. So we've got a happy square. Whereas for this first example here, if we offset those, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This shape up here is no longer a square. This shape up here is a rectangle. It's a 2 by 3 rectangle. So it's not a happy square, it's a sad rectangle, so we can't multiply it. And please, in your exam, don't say we've got a happy square or a side rectangle if it asks you why we can or can't multiply these matrices. Refer to your dimensions. But certainly as a first port of call for thinking, can they? This is a good way to visualise it. Okay, so in a second we'll have a look at a little activity where you guys can try at home to see if you can spot what these matrices are, whether they can multiply, and what the answers will be if they can. Okay, so on the board we've got 6 questions that we're going to very quickly go through in a second. But first, I think it's time you guys had a bit of a practice. So if you want to pause the video now and have a go at these questions, so you've got 2 jobs for each one. You need to work out if the 2 matrices can be multiplied. So it's going to be a yes or a no. And then if they can be multiplied, see if you can work out what the answer is when you do it. So pause the video now, and in a quick second we'll have a look at whether we can answer these. Okay, so I think it's been a quick second there. Not interested in any of these slow seconds. So let's have a look at this one. So just to start us off, let's just decide if it can be multiplied. So this is a 2 by 2, and the second one's a 2 by 2. So these middle pair are the same. So when we lay these out, we'll have a happy square, so we know we can multiply these together. So what I will do is I will have some working out space up here. So 1, 2, minus 1, 3 times by 4 minus 3, 2, 0. So 1 times 4 is 4, 2 times 2 is 4, 4 plus 4 is 8. Minus 1 times 4 is negative 4, 3 times 2 is 6, negative 4 plus 6 is 2. Minus 1 times minus 3 is plus 3, and then we times by add the 0, we get 3. And then 1 times negative 3 is negative 3, again, times by the 0 just gives me negative 3. So the answer to this one is 8, negative 3, 2, 3. So well done if you managed to get that right at home. And if you are playing along at home, in the comments, just let me know if you did get them right or wrong. And if you think I've made a mistake somewhere, because I'm not infallible. Let's move on to the next one. So, okay, so let's just double check. Can these be multiplied? So we've got a 3 by 1. Remember, it's the height first and then the width, times by a 1 by 2. So we can multiply them together. That's exciting. So now let's work out what the answer is. So we get 1, 2, 4 times by 3, 6, and yeah, we do get our happy square. So it's going to be quite a big matrix. This is going to be a 3 by 2 matrix, but none of the calculations are going to be particularly tricky here because they're all just single multiplication. So 1 times 3 is 3, 1 times 6 is 6. 6 and 12, 12 and 24. So our answer is 3, 6, 6, 12, 12, 24. Easy. Okay, so now let's have a quick look at this next one. So the first matrix is a 2 by 1. The second matrix is also a 2 by 1. So we've not got a match there. So that one can't be multiplied. So we simply say that there's no answer, it's undefined. The same way division by 0 is undefined. It's not because there's a particular problem with that, it's just that it doesn't really make sense. The same way here, saying we're going to multiply these just doesn't make sense with the algorithm we've got for it. It doesn't work. Okay, let's have a quick look at this one. So this one is a 1 by 2 by a 2 by 2, and they are the same, so they'll multiply. So let's go to our working out box. So we offset the second one. 6, 2, 1, 4, 3. So then going to be a 1 by 2 matrix here. Let's work it out. 2 times 3 is 6. 6 times 4 is 24. So that gives me 30. 3 times 1 is 3, 6 times 3 is 18, so that gives me 21. Perfect. Okay, let's have a little go at E. So you should notice that D and E are just the same multiplication, but the other way around. Let's have a quick look here then. So this is a 2 by 2 matrix times by a 1 by 2 matrix. So we've not got a match, so they don't multiply. So I suppose this, more than anything else, is a really good reason as to why matrix multiplication isn't commutative. The order does matter, to the extent that even if we've got two matrices that we can multiply one way around, we might not even be able to multiply them all the other way around, regardless of whether the answer will be the same. There's just not going to be an answer if we do it the other way around. Good, and then this last one, so F, let's just check if it will multiply first of all. Well, this is a 1 by 3, and this second one is a 3 by 1. So it's looking like it should go because they're the same. And let's work it out. Now this one's a little bit trickier because it's got an A in it. Absolutely no problem here though, because if we know how to multiply algebraic expressions together, especially if they're just A and A. So let's do 3A2 and 0A1/2. 3 times 0 is 0, A times A is A squared, and 2 times by 1/2 is 1. If we add those things together, then our answer is just A squared plus 1. So we're going to get a little 1 by 1 matrix, and the only entry in that matrix is A squared plus 1. Good. So this is already turning into a pretty long video. I just want to go through one more example where we have a look at some of these algebraic expressions and what we can do to work with those. Because some of the questions you might get and some of the things you might need to work out what the matrix is before we multiply it if we're given the answer. So you might need to work backwards. So we'll have a quick look at an example of that in a second. Yeah, well done. Again, if you did manage to get those right, congratulations, because it's not an easy thing to do. Okay, so on to our last example now. So in this one, we're looking at two matrices being multiplied together, but we're told the answer, but we have to find some variables in each of the matrices that we don't know. So if you want to pause the video and have a go, now is a good time to do that before we go through how to do it. So with any topic in maths, if you've got some algebra involved, a good strategy is to try and write the same thing in two different ways. So here we've got this multiplication, and we want to try and write the answer to that multiplication in two different ways. Now we're told that one way we can write the answer to this multiplication is this matrix here. Just by what the question tells us, this matrix is the answer to this multiplication. But we've also got another way we can write the answer to this multiplication, and that is to use our method that we've been looking at in this video. So let's do that now. So this first matrix is 2A, 3B. And remember, we offset the second matrix so we can work it out. Now here, what I've done is I've made the second matrix a little bit wider so that we've got space for the algebraic expressions in the answer of this matrix multiplication. So here, this one is going to be 2 times A and 2 times A, which we add those together, we get 4A. This entry is this column times this row, which is 3 times A plus 2 times B. And here you see why it's a good idea to make these a bit wider, so we've got a bit more space. Here we've got 2 times negative B is negative 2B, and 5 times A is 5A. And then last but not least, we've got this guy, which is 3 times negative B, which is negative 3B plus 5B, which just leaves me with 2b. So because this is the answer to this matrix multiplication and this is the answer to this matrix multiplication, we can set those equal to each other because they have to be the same. So we get negative b, negative 26, 10 and 16 is equal to 4a. I'm going to write this the other way around, so the positive things first. It's just a little bit nicer that way. 5a minus 2b, 3a plus 2b, and then 2b. Now, a property of matrices, a really important property of matrices, is that for two matrices to be the same, all of the individual entries must be the same. So I know that this minus b has to be equal to this 4a. And I know that this negative 26 has to be equal to this 5a minus 2b. Now there's one, which is a really nice, easy starting point. I'm wondering if you can spot it. Have a look. Exactly, yeah, this guy at the bottom right is a really good starting point because it only involves one of our two variables. So let's look at solving this equation. So remember, if these matrices are the same, then 16 has to be equal to 2b, which tells us quite nicely that b has to be equal to 8. So let's just write that up here. B is equal to 8. So now what we can do is we can go through our matrices and swap all our b's with 8, because that's what this allows us to do. So this negative b here turns into negative 8. This negative 2b here turns into negative 16. This 2b here turns into 16. And this 2b here turns into 16. So now, which one of these is the next one that we should be looking at? Which one of these is the easiest to try and work out what a is? Exactly, we're looking at these top left ones, these orange ones. So we get negative 8, which is this entry, is equal to 4a, which again quite nicely tells us that a is equal to negative 8 divided by 4, which is negative 2. So I'll write that up here. Now the last thing we want to do is just check to make sure I've not made any mistakes. So let's just substitute this negative 2 into our two matrices to see if it makes sense still. So 4a times, if a is negative 2, 4 times that is negative 8, which is correct because that's negative 8. 5 times negative 2 is negative 10. Negative 10, take away another 16 is negative 26. So I'm happy there. 3 times negative 2 is negative 6. And 16 take away 6 is 10. So I'm happy there. And then 16, I already know, is equal to 16. There we go. So that's probably the hardest sort of question, just on pure multiplication, that you'll get at GCSE further maths. Some of these problems will mix this in with some of the transformation stuff we've looked at. But again, I think we've covered that fairly thoroughly in the other videos. So yeah, if you managed to follow along with that, if you tried this at home and got it right, well done, because that's not an easy problem. Good job.